In section 11.4, we're looking at derivatives. And it's really the rate of change at a point, but on a practical basis, what happens is we're taking a curve and sort of reducing it or simplifying it to a straight line. And then we'll work with point and slope with it later too. And I want to show you first and make sure you're really comfortable with the fact that there's a shortcut for doing it. The textbook shows a method, but there's a very specific shortcut to doing it, which is a lot easier. You still have to use that method for some things. But look at what happens here. If this is the function, you get the derivative, and it's written this way as f prime. So you use that prime symbol. And you get that by taking the exponent, multiplying it to the coefficient, so it's 2 times 1, and reducing the exponent by 1. So we're bringing the 2 over here and doing 2 minus 1, so we get 2 times x to the first power. In this one, the exponent is 1. So 1 times 1, so it's like x to the first power. So we'll bring that down to the one that's here, so it becomes 1 times 1. Oops, it'll go to 7, so let's make it 1 times 1. And then we're going to subtract 1 from it, so that's going to make 0. And that's what I show here, so cross down a little bit. Minus 1. 1 minus 1 is x to the 0. So that means no matter what, it doesn't matter. This could have been a 53 here. It would have been 1 times 53, but then it would have been x to the 0. Oh, and so it's a 1. And so that nice easily becomes 1 times 1. Okay, 2x plus 1. That's why we get that derivative. Look at these other examples. These two are just like it. 2 times the 3 makes 6, and reducing it by 1. So this 1 becomes 1 times 2 is 2, and x to the 0 power, so minus 1 makes x to the 0. This one becomes 10x plus 4. This one's a little more complicated, though not much, and there's a note about 9. So 2 times 7 is the 14, so we have 14x. The 1 here multiplies to the 2, so it's 2, and then that becomes x to the 0. And over here, that's reality is that's x to the 0 power. So we take the 0 as the exponent, multiply it to the 9. Well, 9 times 0 is 0, and 0 times anything is 0, so it's just gone. So it just doesn't exist anymore. It's just out of there. So these two become 14x plus 2, and whenever there's a constant, the derivative doesn't include it anymore because the fact that it's an x to the 0 power here. X to the second, x to the first, x to the 0. Then over here, now this one, okay, and let's work this one out. If you are watching this as a video, stop it and do it yourself for a moment, and come back to it, and I'll start in about 2-3 seconds. All right, now, I do 4 times 2, which makes that 8. I reduce that by 1 to make it 3. I'm going to do the same kind of thing here. 3 times the silent 1 makes it 3. And x to the, well, 1 less than 3 is 2, so that should be a square. Here, this is a 1 times 5 makes that 5. But that's going to become x to the 0, which is 1, so I want you to put an x there. And this was x to the 0. 0 times 1 is 0, and that's just gone. So that is the derivative for here. So I show here's the originals, and here's the derivatives of it. Okay, now let's look at this problem where we are going to get the equation of a tangent line. That means this is some form of a parabola with something, and it's in some shape. Well, what we want is the place where there's a tangent that goes along. It just touches it at one point, and that's the point. So what we do is we take this and find that this curve here is x squared plus x, give or take. I just make it a wild guess, but just so that we're able to get to show tangent here. So that, the derivative of it is 2x plus 1. Notice what I then do is I'm putting the x value of 2 into here. So when I do the derivative with 2, I put a 2 in for the x. And 2 times 2 is 4, plus 1 is the 5. That 5 is the slope for the equation, and the rest of it becomes something you've done many, many times, where you use the 5 as the slope, and plug in the point you were given in order to get the y-intercept of -4, and there you have a slope and a y-intercept, and that's the equation of that line. Now, obviously not, 5x minus 4 is 5 is a slope going like that, but this just illustrated the concept of a tangent line. Well, now, you don't need to draw anything to get this. Go ahead and find the equation. Yes, find the equation of the tangent line of this that is at that point. I stop the video and do this, and I'll come back to it in just a couple of seconds to show you how it's done. All right, you're back now. Thank you for coming back. So what I need to do first is to find the derivative, and I'm going to do 2 times 3 to make that 6x, and 1 less is 1. The 1 times the -4 is -4, and no x now because it's x to the 0. And that's it, just 6x minus 4. Then I'm going to find that derivative for the 1. And that means I'm going to do 6 times 1 minus the 4. And then 6 take away 4 is a 2. So that allows us to have a slope of 2. And I can do y equals 2x plus b. So there's my slope. And I have the point here to put in as 5 equals 2 times 1 plus b. So I'm going to have 2, bring it over as minus 2, so b is equal to 3. So that means we have y equals 2x plus 3, and that is the tangent line to this curve. So wherever this is curved, and this is the tangent line, like here's the curve, and here's the tangent line, give or take. That's the concept. We now have the equation of that line. Now, let's look at an average rate of change. So, this is similar to a textbook problem where it's a 5 instead of 6, but it's the same idea. So I'm going to go through and do it here. And now we will have to use the formula that the textbook uses, partly for finding the derivative, but here we'll have no choice to use it in order to work with these other ones. So I am telling you that we have a cube where each side is 6, so it's x to the 3rd power, and a equals 6. And as it changes by 0.1, as the height changes from 6 to 6.1 and 6.01, well, what we're going to see, because all of them would be changing, height, length, and width, all of them would be changing. We're going to use this. We're going to do the function when it's 6 plus the h. Okay, so 6 plus 0.1. Okay, 6 plus 0.1 minus the function at 6. So the function, whoops, all of that over 0.1. Okay, so I'm going to calculate it here with the function of 6.1 minus the function of 6 over 0.1. So that means I would put that in there, 6.1 cubed, and then minus 6 cubed, and divided by 0.1, and I will tell you what that comes to. That equals 109.8. Now, I forgot to say all here, and I guess I should say it, that that's centimeters. So that means it's centimeters here. Okay, so when I find that, that's centimeters. Oh, but it's cubic. Oh, no, it's not. It's inches. I'm looking wrong at my notes. So it's inches, which means it's cubic inches. So the volume increases by that amount between 6 and 6.1. Okay, now let's do it with H2. Okay, so we're going to do, I'll do this as B. So the function 6 plus 0.01 minus the function at 6, and then we're going to divide that by 0.1. So when you calculate that, 6.01 cubed, because it's x cubed, so the function with that, we'll put in 6.01 cubed minus 6 cubed divided by, oops, and I need to put the same one now. That was 0.1 and 0.1, this one's 0.01. So important thing to not make a mistake on. This one's going to equal 108.2 cubic inches. Not that much difference, actually, and then it's a very small increase anyway, all right, well, from 0.01 to 6.1 to 6, or 6 to 6.6 to 6.1, 6 to 6.01. Okay, and then let's also figure out what it is the function of x is equal to x cubed. Let's find the derivative of it. So that means we'll bring the 3 down in front times 1, so that's 3, 1 less exponent, and then we will find that for 6. So 6 squared is 36 times 3 is 108 cubic inches. So when it's at 6, it's 108 cubic inches. Oh, actually, as we say, the change when it's 0.01 brings us up to there, and then up to here. So you need to be ready to perhaps figure out the average rate of change. I think it's especially interesting to have this idea that's coming next, which is instantaneous velocity. So I'll tell you right now that I like this one that's coming. Okay? Which tells you want to make sure you're very comfortable at figuring this out. And it's all going to be based on using the derivative for it. So we have this equation showing the arc, or how the movement is of something that's in flight or is going in a parabola form. And because it's negative, we know we're going like this. Oops, yeah, straight. So something like that. We're going to find the velocity at 2 seconds. So we're not going to find the place, and we're not going to find, the distance. What we're looking for now is velocity. And that's part of what calculus really is good for. More than just place or distance. Now we're going farther into the speed, the velocity of something, the change of it over time, or as it moves from one velocity to another. So we're going to find the velocity at 2 seconds, and then we're going to find the velocity when it hits the ground. So what we do is we first find the derivative. So I'm going to take the 2 down and multiply it, make it negative 24t, but no longer squared. I'm going to take the 1 from here and multiply it to the 36, but the t is t to the 0. And this one we don't need anymore because it's with it next to the 0. All right, so that is our derivative. So now we're going to find out at 2 seconds what will be the velocity for it. And this is how we find that velocity, is we use the derivative. So we put a 2 in here, we get negative 48 plus 36 becomes a negative 12, and it's feet per second. So what I should have said here is feet. I guess I didn't. So find the velocity. So now I'll tell you it's negative 12 feet per second. The negative means it's going down, and it's going down very fast. 12 feet a second is pretty fast. Now, let's also look at this. What we're going to do is find when it hits the ground. So finding hitting the ground, well, when it hits the ground, that means that the place, the x is 0. The result of whatever time it is going to be 0. So what we can do is place this equal to 0. 0 equals negative 12t squared plus 36t plus 120, moving on up. This is no different from what you've done before to find where it hit the ground. So this can be factored when you take out, divide everything by a negative 12, and then factor it, and you're going to get t minus 5 and t plus 2. So that means t is equal to 5 or negative 2. Well, the negative 2 makes no sense, so we can just cancel that out. Now what we're going to do is we're going to take that, we're going to take the derivative, and we're going to put the 5 in, because we found the velocity at negative 12 feet per second. Now we want to know what it is when that was at 2 seconds. Now we know that at 5 seconds it will hit the ground. The velocity, we'll use this form. So g prime 5 is equal to negative 24.5 plus 36. Okay? And that comes out to negative 84 feet per second as it hits the ground, or I'm going to say at ground impact. So our questions were find the velocity at 2 seconds and find the velocity when it hits the ground. And that's a large part of what you can use the derivative for. So the main things I want to concentrate on from this, besides being really comfortable with how to make a derivative using this format, using the shortcut that I showed you, you take that and make that with it, is to find the equation of a tangent line and to be able to find instantaneous velocity. And there's other things, like I showed you with rate of change, and there's other things in that section, but those are the ones that I am most interested in. And I hope you are comfortable with doing that now and give you a start on AP Calculus when you encounter that in the future.